Mr. Cook. Hello there. I don't know what happened to that. We seem to have lost us in that
This gigantic aerial, nearly 100 feet in diameter, is at Goonhilly in Cornwall, at the high temple of British satellite communications. But even before it was ever built, I could have taken this transistor radio to almost anywhere in the world and switched it on, and immediately I would have been able to hear either music or news. In fact, all the time, we are based in this mysterious form of energy, which we call radio waves. But such is humanity's need for communications, that satellites had to be pressed into service in order to increase the links between continent and continent. Communications these days is a very big business, employing millions and millions of people. Efforts to communicate over greater distances must go back to the very dawn of human history. First by shouting, and then leading to the development of the megaphone, much beloved by power-mad film producers. More seriously, the heliograph was capable of communicating over up to tens of miles under suitable conditions. It worked by reflecting the sun's rays by means of a mirror to the distant receiving station, it of course being necessary to adjust the angle of the mirror in both planes pretty carefully. The return signal, the answer, would be received by a colleague looking through this telescope. The method, however, wasn't really much good unless the sun was shining, which made it rather unsuitable for the UK. However, by 1850, there was one pretty reliable method of long-distance communication. Morse telegraphy proved to be an effective and popular way of sending messages. The Morse key was connected by many miles of wire to an inker machine which printed out a permanent record of the dots and dashes. By using undersea cables, the system even worked across the Atlantic. Hello? Mr. Bell? Mr. Graham Bell, could you just hold on a moment? And since 1876, people have been able to talk to one another using wires. They had the telephone, perhaps only at the office, but not at home. But for long-distance communications, wire were a nuisance, because they were kept on breaking and were even struck by lightning. So clearly, some form of wireless long-distance communication had to be invented. Hello? 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 Paris, 1850. Monsieur Benoit states that two snails once placed in contact are ever after in sympathetic communion. He claims to have passed messages to a fellow Frenchman across the other side of the Atlantic. The snails are placed on similar copper plates with letters all around the edge. When a snail in Paris touches a letter, its sympathetic partner in New York puts out its horns and the letter is received. The medium of transmission is stated to be escargotic fluid, which is a galvano-terrestrial magnetic animal Adamic force. This method wasn't used very much. The real answer lay not in escargotic fluid, but in something just as exotic and delightful, if rather less edible. Victorians were absolutely fascinated by sparks. Scientists soon realized, however, that a spark, far from being a single discharge between 2 points, a discharge of electrical energy, a spark actually consisted of a very rapid oscillation of sparks forwards and backwards like that. Heinrich Hertz, a late 19th century German physicist, believed the oscillating properties of sparks created waves of electromagnetic energy which would spread throughout space in very much the same way as ripples spread out across a pond. So he began a series of experiments which were to have a profound effect on all our lives. Hertz reasoned that as a current in the circuit was surging forwards and backwards at millions of times per second, each surge would be accompanied by a complete reversal of both the electric and magnetic fields around these wires, and that these were precisely the conditions under which some of the energy might be persuaded to be radiated into space. Now, he further argued that the efficiency of this process might be increased by adding these large capacitor plates. In order to make the sparks, Hertz used this induction coil, which is capable of producing somewhere between 20,000 and 50,000 volts. It's really a first cousin to the ignition coil, which is used in every car. But Hertz found that it wasn't so much the difficulty of making the sparks as detecting the energy which had been radiated. In order to achieve this, he turned his mind back to his earlier work on sound, where he'd been able to detect very tiny signals by using the principles of tuning or resonance. Let me demonstrate this principle of resonance. I've got a steel reed here, it's actually a hacksaw blade, which is kept in continuous vibration by means of an electromagnet. Some of the energy from this reed travels down this wooden rod here to this receiver. Now, my receiver is another reed, but at the moment it's not tuned, it's not resonant to the same frequency. If I now slowly make it longer, and you can see the increase in length by watching the black gap at the bottom there, it increasingly comes into tune, the amplitude of vibration goes up enormously, as we can see here. So it's now become a very much more sensitive receiver by virtue of being resonant to the transmitted signal. This is the receiver which Hertz was using. It consists of a wooden frame which carries a single tune turn of wire, which is broken in one place by a tiny adjustable gap. Hertz knew that he was receiving some of the energy being radiated by tiny sparks passing across a gap. Now, these were the very waves which theory had predicted should exist, and which Hertz subsequently showed to share all the properties of light. Of course, we can't see these waves, but with a modern oscilloscope, we can see how they occur in rapid bursts. Even though Hertz had conclusively demonstrated the existence of these waves, he did not believe them to be of any practical significance, largely, I suppose, because of the short range of their effects. Soon, scientists all over the world were repeating his results. It was left to a young man, who wasn't even a scientist, to rescue the phenomenon from oblivion. He is the one who most people think of as being the inventor of radio, and he lived in Bologna in Italy. Guglielmo Marconi was born into a rich landowning family here at number 7 Via della Asse in the spring of 1874. His mother Annie was a member of the famous Irish whiskey family of Jameson. Consequently, young Marconi received part of his education in Britain and was fluent in English. The family owned the Villa Grifoni just outside Bologna. Here he began his experiments. Marconi had little formal scientific education, but he was a great experimenter, particularly with everything to do with electricity. In 1894, just before he was 20, he read a paper published by Professor Righi of Bologna University, in which he described the work done by Hertz, who incidentally had died in January of that year. This work so much stimulated Marconi's interest that he decided to try the experiments again. Such was his success that this, combined with his business acumen, very soon made him one of the giants of wireless communication. In his upstairs laboratory, he applied all the improvements which he'd read about, and the results were so good that he decided that he needed more space. So he simply moved all his equipment out into the garden. This is the kind of equipment he used. The sparking coil is connected to a 4-ball Righi oscillator, which was believed to produce more vigorous sparks. Marconi was obsessed with transmitting over longer distances and discovered that by connecting a metal plate strung up fairly high to one side of the transmitter and the other end to Earth, it was possible to greatly increase the signal strength. He used a similar arrangement as the receiver, which itself was much better than Hertz's original wire loop. It consisted of a sensitive device called a coherer, which made a bell ring when a radio wave was received. By making careful adjustments to his equipment, he was able to transmit over greater and greater distances out into the garden. His brother used to wave a white handkerchief whenever he received a transmission. So far, all the experiments had been in line of sight. That means it was possible to see the receiver from the transmitting station. But Marconi believed that providing you used long enough waves, it should be possible to transmit around quite large obstacles. So he sent his brother, with a receiver and armed with a hunting rifle, over the hill at the back of the Villa Grifoni, a distance of more than 2 kilometers. This was a crucial test. Marconi began to operate the transmitter with a Morse key. To his great satisfaction, the experiment had worked. He could transmit beyond the line of sight and now felt ready to seek potential users. He approached the Italian office of Post and Telegraphs, but they politely turned him down because the technology of wire telegraphy was well established and they saw no advantage for the new method for communication between fixed points. After a family conference, it was decided to send young Marconi to England. Britain was still the workshop of the world with 2 large navies and the problem of communication at sea. Influential relatives in London soon put him in contact with William Preece, chief engineer to the post office. As a result, Marconi was soon making arrangements for a full-scale demonstration to the Army and the Navy. Salisbury Plain in Wiltshire was the chosen site, and young Marconi gave an impressive show with equipment similar to his Bologna experiments. That Marconi system worked was clear for all to see, but that wasn't quite good enough. To the military, with security in mind, there was concern that the signal spread out or was broadcast in all directions and could be received by anybody with quite simple equipment. Hertz had shown 10 years previously that radio waves could be reflected and focused just like light. In this torch, the light from the bulb is concentrated into a narrow beam by the parabolic reflector behind it. With metal reflectors exactly like these, Marconi hoped to overcome some of the Army's reservations about the system and show it was effective for secure point-to-point communication. These members of the Royal Corps of Signals are attempting to measure the width of the beam produced by the reflectors. They have been able to show that Marconi had the principles right and that some concentration of the waves was produced. Obviously, the narrower the beam remains, the better the security and efficiency of the system. Today, parabolic reflectors, which instantly only produce well-defined beams if there are many wavelengths across, are a very important part of microwave links and satellite communications. For Marconi, however, the way ahead lay with his elevated areas and his earthing system. Both systems form the subject of the world's first wireless telecommunication patent application, which Marconi filed on June 2nd, 1896. This was quickly followed by the formation of his wireless telegraphy and signal company, later the Marconi Company. The press loved Marconi's showmanship. Hardly a week went by without some news stories. Royal interest may have helped to sell newspapers, but it didn't sell many wireless sets. So by 1901, the fledgling company was desperately short of money. At this very critical time, Marconi decided to attempt the coup of transatlantic communication, a distance more than 20 times as far as anything which had been attempted previously. And moreover, through a thick mountain of water, 200 kilometers high, because of the curvature of the Earth. This seemed an absolutely harebrained proposal to almost everybody concerned. This point of view was shared by Marconi's board of directors, but eventually he managed to persuade them. This memorial marks the site of the first transatlantic radio transmitter here at Poldhu in Cornwall. These ruins are all that remains of a very considerable investment. £50,000 was really a lot of money in 1901. It was used to build a 25 kilowatt generating station and a 61-meter aerial of very advanced design. On September the 17th, the worst scale in living memory struck the station, and all 20 masts collapsed in a shambles of broken timber and tangled wire. A new temporary area was erected. Under considerable pressure from the shareholders, Marconi decided to attempt one-way communication from Poldhu to the nearest point in North America. With 2 assistants, he set sail on November the 27th for Newfoundland. They arrived on December the 6th and chose Signal Hill as the most suitable site to receive the transmission. Their equipment was set up in an old military hospital. Imagine their states of mind. Almost everything had gone wrong at Poldhu. Here in Newfoundland, there was not a solitary aerial mast. Fortunately, they had taken kites to try and fly an aerial in the foul Atlantic weather. By December the 9th, everything was ready. A cable telegram was sent to Poldhu. The Morse letter S, just 3 dots, was to be transmitted continuously for 4 days, starting on December the 11th. By the morning of the 11th, they had already lost 1 kite and 1 balloon. They had better luck with the 2nd kite, although it was plunging and rearing violently. The next day, the weather was just as foul. Through heavy interference, Marconi and his assistant Kemp strained to listen to the rhythmic dots of the letter S. Finally, at 12:30 p.m., Marconi was at last convinced he could pick out the signal. He scribbled in the notebook. It simply read, signals at 12:30, 1:10, and 2:20. Marconi's name would be linked forever with the greatest development in communications the world has ever known. What scientists didn't know at the time was that a layer of ionized gas in the upper atmosphere acts just like a huge mirror, reflecting the radio waves back to Earth. Further tests at sea proved long-distance wireless communication beyond all shadow of doubt. Soon, shipping lines and navies all around the world were equipping themselves with increasingly reliable and sophisticated apparatus. A new industry had been created, and the ether was full of dots and dashes. If I had been the wireless operator sitting in my radio cabin on board ship, I would have received the Morse, decoded it in my head, written down the message, and almost certainly replied directly. I might even have recognized my colleague at the other end, because the styles of sending Morse became so distinctive that those in the know could recognize them just in the way which you can recognize my voice. The proceedings were pretty informal, and mixed in amongst the official messages there must have been a good deal of social chit-chat. This was certainly so on December the 24th, 1906, and mixed amongst the seasonal greetings I suddenly heard this.
Hello? If anybody hears me, please write to Mr. Fessenden at Plant Knock. Thank you.
Now, what had brought this marvel about? Technology had improved not only the receivers, but it also improved the transmitters. Simple spark transmitters produce irregular bursts of radio waves, good enough to carry more signals, but totally inadequate to carry the subtle variations required for voice transmission. A cleaner and continuous source of high-frequency radio waves is required. The level of this carrier wave is varied or modulated by the much lower voice frequencies. The radio wave then carries the speech and music in a piggyback fashion. This high-frequency generator produces the clean, continuous carrier required for voice transmission. This rotor is intended to rotate at 20,000 revolutions per minute and produces an AC current between 50,000 and 100,000 cycles per second. In principle, it's not so very different from the kind of generator which used in a power station, which however only produces an AC current of 50 cycles per second. Whilst voice transmission was perfectly possible using a set of this kind, it didn't really become at all common until the valve was invented and had been persuaded to oscillate.
It's the national program from London. We begin this evening with a concert by the Gershon Parkington Quintet, who will play Liebestraum, Love's Dream by Liszt.
It's one small step for man, one giant leap for mankind. Surface is fine and powdery. I can pick it up loosely with my tool.
In the early days of radio, much of the traffic was rather slow Morse. As the technology improved, it became increasingly devoted to voice communication. These days, an increasing proportion of the traffic is data, including the kind of communication being provided by this aerial. Even on this little radio, if we scan the frequency bands, we come across whole regions where there was data traffic. Now, if we slow this down, it would sound again rather like Morse. It's now nearly 100 years since the first spark sputtered into life as a message. Those hesitant signals, radiated out from the Earth with the speed of light, are now many billions of miles away out in space. Out beyond the planets, past many stars, some perhaps with solar systems like our own, containing planets similar to our Earth, with thinking inhabitants. Even now, these beings may know that they are not alone.
Hello? If anybody hears me, please write to Mr. Fessenden at Grant Park. Thank you.
National programme from London. Now you're going to hear the first performance of the new BBC Dance Orchestra, directed by Henry Hall. It's just the time for dancing. Tomorrow is today. Go where the music's calling and dance the blues away. The world that lies before you is one big